first let us check how much of energy that is required by the heater 1, the reactor 1, the heater 2 and the distillation column reboilers. So for that we use a heat mixture. Okay, so this is a heat mixture. We keep it over here. Now let us connect the heat streams. So connect these streams over here. Connect this stream. This is the reactor stream. Okay. So okay, so let us name it as heat or Q heat 1. Let us name it as Q react 1. Okay. Then collect the heat from here also. So term it as Q heat 2. Okay. So we are collecting the heat from heater 1. So this is the heat requirement of heater 1. Q heat 2 is the heat requirement of heater 2. And Q react Q react 1 is the heat requirement by the reactor 1. And we have two more heating possibilities. There are two reboilers over here. So that also we collect. So this is the first one, reboiler heat stream. Q rib 1 and this one. Q rib 2. Okay. So that way we have collected the heat streams from heater 1, heater 2, reactor 1, reboiler 1 and reboiler. From all of them, we have gathered all the heat requirement. And that total heat requirement, we are sending it to the cooler. So we'll connect it from here and attach it over here. Okay. That means all the heat requirement, we are giving it to the cooler. You have total around 40 megawatt, right? If we remember correctly. Yeah. It was 40 megawatt of heat that cooler is able to provide. So it can cater to all the heaters, reactor and reboiler. Okay. All the needs can be catered by this. Once we have connected this, then we do not have any information over here. We can give only the pressure information because now the temperature of this will be guided by whatever the amount of heat that it has supplied to these heaters. Okay. So let us now run the process. It has come to 28. Now come to this conclusion that after giving all the heat as it was required by them, you come down to 28 degrees centigrade as a flue gas. Now, flue gas 28 degrees centigrade is not something that we generally come across. Temperature of flue gas will be quite high. Now, the second problem says that how much methane can be saved if the heat of reaction and heat of flue gas are recovered and used in the process. For heat recovery from the flue gas, assume that they are vented to the atmosphere at 150 degrees centigrade. So let us do one thing. We will fix it at 150 degrees centigrade without heat integration. And after heat integration, let us see how much energy savings that we are achieving. Okay. So for that matter, here also you can perform the retuning of methane flow rate in order to fix the temperature of flue gas by using another design spec. I leave it up to you for your practice problem. Now let us inspect the whole process plant and take some heat recovery measure. Here we find that we are using a heater which is increasing the temperature from 25 to 220 degrees centigrade, whereas this stream is losing heat from 427 degree to 25 degrees centigrade. So why can't we use this stream to preheat this stream, the feed stream, before it goes into the reactor? That way we can save some energy over there. Not only that, we can preheat this air. On the other hand, here we find that the pump out is at 25 degrees centigrade, which is being heated up to 93 degrees centigrade before it enters the distillation column 1. So here there is an opportunity to preheat using some of the hot stream. So why can't we use this particular stream, that NMP stream, to preheat it? Because NMP stream is at 204 degrees centigrade. So we can surely do it to preheat, right? So what we will do, we will clear this heater and we will clear this heater. Instead, we will place a couple of heat exchanger. So this is the first heat exchanger that we can place over here. And there is another heat exchanger that we can place over here. Here, we can place another heat exchanger to preheat the air. And finally, we can place a heat exchanger over here to preheat the distillation column inlet. Now we have to connect the streams. So reconnect this to this destination, cold in And then we connect, sorry, it is a material stream. So connect this one with this, and then reconnect this one with this source. Okay. So cold feed, we are passing it to the first heat exchanger. Then it will go to the second heat exchanger, and it will be over here. Okay. Or for that matter, we can delete one heat exchanger from here. Just leave it with this. So connect it with this one. Okay. Now, this one also, we will connect this stream with this one, and we'll connect these two material streams. So basically, we want to preheat the feed and air with reactor out. Okay. How we'll do it? We shall reconnect this at the destination of here, because this is a hot stream. Okay. So we are placing it over here. Then outlet of this hot stream, we will connect it over here. Okay. And then outlet of this hot stream, we'll send it back to the cooler. Now see the logic. We have a heated stream over here at 427 degrees centigrade. So that we are feeding in to this heat exchanger in order to preheat this feed. Outlet, we are feeding it to the heat exchanger, and whatever heat being lost over here to preheat this air and feed, rest of the thing we are sending it to the cooler. Okay. Now, what we can do, we can set the values over here later. Similarly, the bottom stream, we can connect with this. This is the hot fluid. Okay. This one will connect to the cold required, and this is the source. So pump out is going in and being heated through this bottom two. Obviously, there will be an outlet for bottom two, and this is the outlet for bottom two. Okay. So we can name it as NMP recovered. So this is NMP recovered. So this is the NMP feed, and this is NMP recovered. Okay. Now here we have to set the design temperature, which is cold stream outlet temperature. It is 93 degrees centigrade. Okay. So we have set it as it is. And here again we have to set it as 220 degrees centigrade. That is the cold stream outlet temperature, which is 220 degrees centigrade. So it has preheated up to 220. And then this one. Okay. This one we will preheat up to, say, say 90 degrees centigrade. Okay. So that way everything is done. Or is anything left out? Let us see what is left out. Okay. So actually these streams we have to delete because they do not exist anymore. Okay, heaters do not exist anymore. So we have only reactor outlet and 2 reboilers outlet that we are now working with. Okay. So we have done some sort of heat integration. Okay, some sort of heat integration that we have done. Now run it once again. Okay, here some temperature crossover has been detected. So maybe we cannot run up to 90 degrees centigrade. So let us make it up to 50 degrees centigrade and see how it works. Or we can just delete this one. Okay. There is no point in preheating the air at this moment. And instead you can just connect it with the cooler. So let us keep it very simple and run it. Yeah. Now the results are available. Now we are not using any heat exchanger network, and one thing that you can notice that the heat recovery earlier it was around 36, but now it is 33. Basically we have used some of the amount of heat over there within. Now whatever the heat integration that we have done in this whole exercise, that has been done randomly because we have got a heated stream over here and we found one stream to be preheated, so we just coupled them together in a heat exchanger to exchange heat. Similarly, we have coupled that pump outlet with the reboiler outlet of the second column. Now, who has said us that that kind of combination is the best combination? Or how do we know that there cannot be any other combination of heat exchangers which, if we connect with different streams in a different manner, that will give us a better energy savings? So for that, we can perform the energy analysis. Okay. Now, you will find some button over here called activation dashboard. Okay. So here you will find the energy savings button. So if you click on this button, then it will do certain calculation and tell you what could be the amount of heat that you can save. And it says 2.7 into 10 to the power 6 calorie per second. That means 37.08% of energy savings is possible. That's what it suggests. Now, how is it possible? You can check it in the energy analysis button over here. So it will give you the details of that. Now here it will just give you the details of how much energy is required in the current state and what could be the target. Okay. Target means in the best possible run of the system with most energy saved, that is the condition we will call a target. And there it will talk about the savings potential. What is the potential of savings if you use HP steam? What is the saving potential if you use LP steam, air, refrigerant, etc. And total hot utilities, the percentage of savings is 65.56%, and total cold utilities savings is 79.83%. Okay, and there are ideas for changes over here. The combust heat exchanger cooler. Okay, it is giving some idea over here. Now, the saving potential is given in this table in a nutshell, but actually the Aspen Plus does a lot of calculation in order to arrive at this table. Now, the question is, how do you know what is the best possible heat exchanger network that will give you the maximum savings? For that, there is a technique associated with this that is called pinch point analysis. In the pinch point analysis, it determines the thermodynamic feasibility of the heat exchange and it helps in heat integration studies. So basically, this is a hot stream, this one, another hot stream, this is another hot stream. On the other hand, this is a cold stream, this is another cold stream, this is another cold stream. So the entry point and exit points of all the hot stream and cold stream can be determined from the process. And one can find the diagram in this manner, and this is called the pinch point. Okay, so the aim of the pinch point analysis is to find out the pinch point. So there are three basic pinch rules actually. The basic pinch rules are: heat must not be transferred across the pinch, and no external cooling is allowed above the pinch, and no external heating is allowed below the pinch. I will give you a small idea about how the pinch analysis works. If you have a set of liquids which are hot stream, say you have a series of hot streams like H1, H2, H3 and so on, and if you have a series of cold stream like C1, C2, C3 and so on. So what you can do, you can create a table of this nature. Okay, so here you will find the H1, H2, H3 and so on, C1, C2, C3, and here you will find the temperatures of entry and exit. So entry and exit temperature. So hot stream, obviously it will be higher, entry will be higher and exit will be lower. For cold stream, entry will be lower and exit will be higher, and there will be the enthalpy that is transferred, the heat released by the hot stream or heat taken up by the cold stream, and from that you can find out MCP. Okay, so MCP is equal to Q by the delta T between these two temperatures. And so this is very important. So you can calculate the MCP for each and every stream like that. Okay, and you have to identify all the individual temperatures of them. Okay, so whatever the temperature limits that you have, those temperatures you have to identify, and then you have to create a table of this nature. In that table you will have parallel lines like this which represent individual temperatures. Okay, so these are the individual temperatures line. So maybe it is T1, this is T2, this is T3 and so on. And you have to identify the heat streams. So suppose the H1 is decreasing from the T1 to T5. So you will have this kind of line. Okay, H2 may be another heat stream whose temperature reduces from this point to this point. Okay, cold stream C1, this temperature rises from this point to this point. Next cold stream, the temperature rises from this point to this point, and so on. So all the process streams you can represent on this chart within the parallel lines of temperature. Now you have to count the total heat content within each and every temperature gap. So suppose in the first temperature gap, we have only one stream that is active over here. So you can say that only MCP of only this one will be active between these two temperatures. Whereas for the second gap, we have 1, 2, 3. Three such streams, they contribute into that temperature gap. So MCPs of all of them should be counted together, multiplied with the temperature difference. That will give you the heat content within that temperature gap. Similarly, each and every temperature gap, you will find out the Q. Now, some of them will be positive, some of them will be negative. Okay. And then you have to study all the heat contents and find out the lowest one. Okay. So lowest amount of heat, whatever it might be. So that amount of heat you need to provide from outside. Okay. And that is the pinch point. I mean, if you optimize the network properly, then that is the highest amount of energy that you have to provide into the system. Now, fortunately, Aspen Plus has the capability of doing this pinch analysis, and it can suggest you the designs. Now here you can see show details in Aspen Energy Analyzer. Now Aspen Energy Analyzer is a separate platform altogether. It is connected to Aspen Plus, so anyone can call Aspen Energy Analyzer from within the Aspen Plus. But once you press these details, Aspen Energy Analyzer will open up in a new platform and it will show you the details. So suppose you press the details over here, it will give you some warning message, but you just press yes over here. Yeah. So this is the Aspen Energy Analyzer. Just like you have Aspen Plus V14, you have Aspen Energy Analyzer V14, version 14. Just look at it. So this is the network cost indices and this is the network performance. Okay, this is the summary. This is the heat exchanger. This is the utility. Okay, everything has been given. The worksheet has been given. Heat exchangers given. The details, everything details they have given. This is the target that needs to be achieved. You can see the pinch point will be somewhere over here. So this is the simulation base case. Okay. And just now I was explaining you how for different temperatures, you can see the temperatures over here. So this is 175 degrees centigrade. This is 35 degrees centigrade. This is 2037 degrees centigrade. This is 250 degrees centigrade, etc. For LP steam, HP steam. Okay. So for various streams and various temperature level, we have this kind of connections. Now, this is not the best connection because we have energy savings opportunities of over how much? If you remember that properly, it will be somewhere around 37%, right? So what we will do, we will check it once again. The Aspen Energy Analyzer. Go to scenario. In the scenario, it will ask to recommend design. Now, this is the composite curve. Okay, composite curve. And the pinch point will be somewhere over here. Here, you have the option for recommend design. Just press recommend design and these are the preview input. Solver option 10, maximum 10 designs will be given. So just press solve and find design. And you will find one by one the designs are given over here. And each one of them, you can see, each design is different. So that way, 10 designs are given over here. So you can choose any one of those designs. Okay. Suppose you choose the design 5, and these are the heat exchanger points. Okay. So if you want to know the details, just double click it and you will find the heat exchanger point. So this is the hot stream, this is the cold stream. Entry temperature of hot stream is 185.3 and it is exiting at 185.2. The cold stream, it is increasing from 25 degree to 110 degrees centigrade. Okay, so what will be the heat duty and what will be the area of heat transfer? Everything has been given over here. So this entire calculation has been done. So each and every hot stream and cold stream points can be observed from here. So this is the connectivity of them. And area per shell. Okay, everything is good. Number of shells in series, number of parallel shells pass, LMTD, overall U. Okay, so detailed discussion is out of the scope of this one lecture, but interested learners can go through each and every design separately and work on. Now, if you want to perform this design, you have to just pick up from this figure and then place it on your flow sheet and connect as it has been suggested over here, and you will get a good design over there. To get maximum energy savings. Okay, so that way Aspen energy analyzer can be used, which calculates the heat exchanger design through pinch technology. With this, we come to the end of this lecture. I hope you have enjoyed it. We'll come back with yet another interesting lecture very soon. Thank you.